Cahit Bartu Yazıcı, and today I will talk to you about using genetic algorithms in Adams Python. I have been working as a modeling and simulation engineer at FNSS for almost 4 years. FNSS is a joint venture between Neural Holding and BA Systems. FNSS produces land mobility vehicles, armored vehicles, a variety of vehicles, including tracked and wheeled vehicles. So today, after a brief introduction, I will go over genetic algorithms and how to use them in Adams. And then we will conclude with 2 case studies. So, aim of this work is to create a method to perform optimization studies in Adams using genetic algorithms. We are using genetic algorithms with Python in Adams, and as I said, we are going over 2 different case studies. The first case study is wheel steering angle optimization of an 8x8 vehicle, where we try to minimize the turning radius and tire lateral slip angles of the vehicle. And the second case study, we are trying to find a steering angle input for an 8x8 vehicle so that the vehicle completes a not a lane change maneuver. So, what are genetic algorithms? Genetic algorithms are very powerful optimization tools that were inspired by the nature. They are very powerful in terms of their randomness. They don't get stuck in local minima as much as some other optimization algorithm does. So this is a basic visualization of different optimization algorithms. The first one is the brute force method, where we try a bunch of different solutions and we try to pick the best one without learning anything about the system. The second one is derivative-based optimization. Derivative-based optimization is the most popular optimization algorithm there is. In this one, we evaluate a solution and then we calculate the derivative of that solution. That derivative tells us where the local minima is located at, which is very useful. But as you can imagine, calculating the derivative can be very hard, and these algorithms can get stuck in local minima. And genetic algorithms are actually a derivative-free optimization algorithms where we try a bunch of solutions at once called the generation, and then we learn from these solutions, and then we try to make better guesses in the next generation. So what are the components of a genetic algorithm? As I said, genetic algorithms create batches of solution called a generation. A generation consists of different individuals. These are our candidate solutions, and each individual consists of different genes. These are our optimization parameters, and we evaluate each individual and calculate the fitness value. This is the indicator of how good a solution that individual is. And so how does a genetic algorithm work? So we randomly create an initial population, and then we calculate the fitness values for that generation. And then we go over our termination criteria. If our termination criteria are met, then we are finished. But if our termination criteria are not met, we go to the process of creating a new generation, which involves selecting, pairing, mating, and mutating to create the next generation. The elite here, after the fitness calculation, is the best solution in that generation directly goes to the next generation without going through mutations, so we don't lose our best solution yet. So let's go to Python and how to use it with Adams. So first of all, why do we use Python in Adams? There are a few reasons to use Python. The first one is quickly checking our model. You can even write a script to automatize this process, and that gives you a list of your model to check parameters. And a second one is quickly modifying Adams objects. This is especially useful in Adams car standard user interface, where you don't have access to every parameter, for example, a marker, but you can change this with using Python. So here I have a very simple example. As you can see, I have a point located at 150, 150, and 0. So in the middle, I have a few lines of Python code. So first of all, I import the Adams library, which is a special library in Python that contains special operations for Adams. In the second line, we assign the point, a Python variable, to an Adams object. This is a string name of our point in Adams, and we create a Python variable. And then using that variable in the third line, we can change the parameters of this variable. So the last thing you can use Python in Adams is the automatization of any process, which is very useful. So how do we use Adams with Python? You can use Python lines by line in Adams command window, as in our example, but this is not a very good way to run a huge Python script. So you can directly import a Python script into Adams. So in this work, I am using Adams 2018, which includes Python 3, and we are using Adams command language commands or .cmd files for some things we cannot do with Python. For example, running a simulation, we are using Adams command language commands. You can find and use already ready to run algorithms in Python with some libraries out there like scikit-learn, or for machine learning, you can use Keras or TensorFlow. But in this work, I didn't have access to internet connection on my workstation, so I had to write my own genetic algorithm, and I use Python 3 and NumPy library for this. So how does the Python and Adams actually interact? So this is the fitness calculation block in Python. We give the individual with our genes to the fitness function calculation block. And here we change parameters in Adams model, and then we call upon .cmd files to run a simulation. And then after the simulation is run, we call another CMD file to obtain the results. This command file actually outputs the results that we want as a text file, and then we read this text file in Python code and obtain the simulation results and calculate the fitness function. So there are genetic operations in this code. Each genetic operation is defined as a function in this work. So the first function is selection. We input the generation to the selection, and then selection process actually picks the individual that are going to be in the next generation. After the individuals are selected, they are given to the pairing function, which pairs these individuals 2 by 2 for the mating process. And in the mating process, we produce 2 offsprings of 2 parent individuals. And then we combine the offsprings and the selected individuals and go through random mutations. In random mutations, each gene of each offspring and selected individual has a chance to be slightly altered, and this actually keeps up the genetic variety and allows us to search the whole search space instead of getting stuck in local minimum. After that, we have our fitness function. Here, actually, we create a Python variable that we attach to a Adams object. And then in the fitness function, we change the individual, the variable with our individual. And then we call a Adams command file to run the simulation and output the results. And then we calculate the fitness function from the simulation results. As an example, in the first case study, we are going to be talking about a steering angle optimization of an 8x8 vehicle. And for this, we need a normalization method because our turning radius and slip angles are very different in magnitudes. So we normalize these values using this function. And then we give biases to normalize turning radius and normalize slip angle, which actually allows us to control the output of the optimization algorithm a little better. And this is our fitness, and this gives us our fitness value. So for the termination criteria, there are a lot of termination criteria that can be used. In this work, we are using maximum generation number, which allows us to terminate the process if it goes on for too long. And then maximum fitness value repetition. This is a very good indicator of our algorithm getting stuck in a local minima and not getting any better because of the elitism. We can stop the algorithm if the maximum fitness value doesn't get better with time. And if we want a bunch of good solutions instead of one, we can use a maximum average fitness value termination criteria. And finally, we have maximum fitness value termination criteria, which allows us to obtain one good result. The value that we choose for maximum fitness value actually indicates our result and where is it going to be. It doesn't have to be necessarily the global minimum. We can choose a local minimum as well. So let's get to the first case study. In this case study, we have an 8x8 vehicle where all of the wheels are steered individually. And we are trying to find the steering angles, maximum steering angles, so that our vehicle turns in a minimum turning radius. And we have low lateral slip angles for each tire. So to be able to do this, I have modified the suspension system where I removed the upper ball joint and replace it with two revolve joints and a dummy part. These two revolve joints allows wheel travel and steering the wheel independently, and we actually steer the wheel with a motion that we give to the joint that is located in the kingpin axis. And then we are ready to perform our optimizations. And the simulations we are running, we are using 8 parameters. These parameters are the steering angles of the tires. These are the values of the motion. We are giving them to our model as a smoothed ramp function to prevent any instabilities in the model. And we keep our vehicle velocity constant at 10 kilometers per hour. We are only interested in the steady state part. So we are not interested in the beginning phase of the simulation. So we are actually disregarding the first 25 seconds of the simulation and taking the results of the last 25 seconds. And then when we run our algorithm using 20 individuals in each generation and fitness values of 0.7 and 0.3, these are the values. The 0.7 is the weight of the normalized turning radius, and 0.3 is the weight of the normalized slip angle, which means we are prioritizing turning radius over slip angle. And we obtain a result, a genetic algorithm result as shown in here. The orange dots indicate the average fitness values for each generation, and the blue line indicates the fittest individual in each generation. So as you can see here, the orange line indicates the trend of our average fitness value. As you can see here, this line indicates that our fitness values, average fitness values, actually are diverging from the solution, while our maximum fitness finds the um, finds the solution that we are looking for. This is because we are using a very aggressive genetic algorithm in this case study, which is a very high risk, high reward genetic algorithm. It finds a minima very quickly, but it does also diverge from in the other individuals. So yeah, and as a result, we have a lower turning radius and lower maximum lateral slip angles than the original configuration, as you can see here. And in the second case study, we are working in a lane change maneuver. So for this maneuver, we have the same vehicle as the first case study, and in this case study, the wheels are independently steered as well, but this is a high-speed double lane change maneuver, so we are not steering the rear four tires, and the front four tires are actually linked together with Ackermann functions in the same axle, and there is a gain between the first and the second axle. So we, with just one steering angle, we are controlling all four front tires at the same time. So in this study, we are trying to achieve, we are trying to complete a NATO lane change maneuver where the dimensions of the road actually changes with the dimensions of the vehicle. And the vehicle speed in this case is kept constant at 80 kilometers per hour. And in this case study, we are using 4 markers for each corner of the vehicle. And we are tracking these markers throughout the simulation. And if a marker in one time step is located between the road boundaries, it gets a 0 as a fitness. So if all of our points stays between the road lines, we get a 0 as a maximum fitness value, which means our vehicle has completed the maneuver without going over the border. But if the point is outside the road boundaries, then it gets a negative value of how further away from the road it is. So the negative values indicate that we are out of the road boundaries, and 0 indicates that we did the maneuver without crossing the borders. So to achieve this, I'm using a function that I derived for this purpose. So this function has 2 parts. The first part is the first lane change steering input, and the second one is the second lane change input. And as you can see here, each side has a drop and a peak, and the magnitude of the peak and the drop changes according to some parameters. And we are trying to find a perfect steering input signal so that our vehicle completes this course. And we are actually trying to optimize these parameters with our genetic algorithm in this case. So we again use 20 individuals in each generation, and then we find the solution after 45 generations, where we get a 0 as a fitness value, which means our vehicle has completed this double lane change maneuver without going over any road boundaries. And here again, we can see the progression of the genetic algorithm. And as you can see here, the fitness value is actually, the maximum fitness value is actually very high compared to average fitness values, and it finds 0 after 45 generations, while our average fitness values are going towards the zero line, which is the result which we want. This is not as aggressive genetic algorithm as before. This is a more yeah. This will find the solution, but it might take a little longer. So as a conclusion, using this method, multi-parameter constraint optimization studies can be performed in atoms. For the steering angle optimization study, we have 10, we are searching for 10 degrees for each tire, and we are using an increment of 0.2 degrees. So we have our solution space is actually huge, and predicted our algorithm has found the solution after 600 tries. Yeah, and this method can be used in atoms for performing other algorithms as well, not just genetic algorithms. You can use other optimization algorithms and machine learning techniques using this method. Thanks for listening. If you have any questions, I can.
Yeah, thanks, Jayat. So this is Hemant here again. If you have any questions based on what Jayat presented, please enter them either in the QA window or in the chat window, and Jayat will be happy to address. Jayad, there is one question on a comparison between the GA method and the gradient-based method. So the question is finding an optimal solution, is it faster in the genetic algorithm method that you used, or is it just that you get to an optimal solution? Is it the probability of the solution that increases, or is it the speed to which you can get the solution?
Yeah, from my experience, actually using genetic algorithm usually finds the solution a little faster. I haven't tried it with so many other algorithms, but yeah, usually genetic algorithms finds the solution in this case a little faster, and usually you get stuck in a local minima with other algorithms for this problem. Yeah,
Okay.
so for finding the solution and for speed purposes, genetic algorithm is better for both of them in this case.
Okay. Okay. There is a question on, so before you transitioned over to the GA method, was there a DOE method that you previously used? So,
Uh, yeah, actually, I used another optimization method before I went with this. We were using Adams 2017, which included Python 2 and scikit-learn library. So I was able to use a algorithm there before we went to Adams 2018, and the scikit-learn library wasn't available in that distribution, so I wasn't able to try it again. But yeah, I did use a library before. Yeah.
okay. And I guess, okay, so this slide, there's a question on which particular, I guess, genetic algorithm package or library from Python you used, and the detail is in this slide, right?
Yeah. Yes.
Yeah. Okay.
This will be.
There's a question on what is the volume of data that is required for this optimization to actually be achieved, right? So how many different add-ins runs did you have to execute?
Okay. In the last slide I've shown you, it was actually 800 Adam simulations were run to find a solution in the steering optimization study, and I believe 800 or so simulations were run in the double lane chain study. So that's 800 simulations.
Okay, okay, and is this typical? I mean, is that the level of simulation data you'd need to generate for these for the kinds of scenarios? Well, from your previous experience, I guess, from I guess non-genetic algorithm-based methods, how would this compare in terms of the volume of data that
Yeah,
you're generating?
from what I tried with the other optimization algorithm study, it converged after 2000, 2000 or so simulations later, and it didn't converge to a solution as good as this one. So that's why I created my own optimization algorithm to find a better one. But yeah,
Okay.
the other one took about 2000 or so simulations.
Okay. And when we spoke about this particular topic, we classified genetic algorithms and the work that we had done under the topic of machine learning, right? So
Yeah.
is genetic algorithm, well, I mean, does it enable machine learning, or is it would how do you, in what family of algorithms would you place GA in? Is it an optimization method? Is it a machine learning technique?
Yeah,
What exactly is it?
I would call genetic algorithms a optimization technique, which is used in machine learning a lot, with especially when you couple genetic algorithms with neural networks. You get a very special, very powerful algorithm called GANs. Actually, it's used for teaching computers to play uh, games, especially used for that. They are very useful, I would say, in terms of finding the optimal solution or searching for something. But when you use them for other things like PID optimization or controller optimization, you can definitely use them for machine learning.
Okay. Okay. So the fitness function that you derived,
Yeah. Uh,
so that is a generic fitness function, right? So that's a generic constraint that could be used for
yes.
GA or other. I mean, it's a generic optimization constraint.
Yes. Yes. This is a very generic fitness function. The example uh, I have shown here is a specific case for the turning radius and the slip angle, but you can add to this fitness function as many parameters as you want, and just add the biases as well. And usually the sum of all the biases is capped at 1, and the each value is normalized so that you can control the results of the algorithm better, basically.
Okay. And so the genetic algorithm, it gives you a set of potential optimal solutions, right? And from there, how did you pick the optimal solution?
Yeah, actually, the genetic algorithms, as you said, gives us a set of, it can give us a set of solution, but for this study, we are interested in only one solution. So we are taking just the best one. But if you're interested in a bunch of solutions, the bunch of good solutions, you can use the termination criteria here, the maximum average fitness value, which will guarantee that you will get an average average result in your final generation. So you would get a all around good solutions in your last generation. You can use it for that as well.
Okay, all right. So these are all the questions that I see, Jayat. So thank you so much for your time. There's one
Thank you.
more. Could you in other than waterlock time, could you tell? I mean, besides how long it took, how long the CPU time was?
Uh, okay, I think each simulation takes about 40 seconds or so, 45 seconds. So it took about 40 seconds times 600 uh,
Okay.
seconds. I'm not
Right. Okay.
so
That
sure
that
about
makes
the
sense.
time.
That makes sense. All
Yeah,
right.
it's so it takes about a 3-4 hours on average for a general optimization study like this. Yeah, about 3 or 4 hours, I would say, in average.
Okay. All right. Yeah, thank you, Jayat. Thank you for the wonderful presentation, and thanks everyone for the questions and the discussion. I'll post a recording of this webinar, and look out for more webinars on this particular topic. Thank you so much. Thanks, Jayat, again.
Thank you. Thank you.